Hi everyone, I'm Kemil and this is Chem with Chem. Now in this video, we're going to be looking at the CSEC chemistry paper for January 2023. That's paper 2, but we're zooming in on question 1. All right, so if you'd like to see the full workout, please check the link in the description below this video. All right, if it is your first time to the channel, welcome. If you're a returning viewer, then big up yourself. Remember to share the value that you are receiving here with others. And don't forget to smash the like button, subscribe if you haven't done so, and turn on post notifications so you'll never miss out whenever new content is added. All right, so let's just get right into it. All right, so first question, and of course, I should not spend more than 30 minutes on this question. So let us just go right ahead. What it says. Define the term normal salt. All right, so normal salt, the salt formed, or we could say the substance formed in all the H plus ions of an acid are replaced by the ammonium or a metal ion. So by a metal ion, by the metal or ammonium ion. That should give us our full marks. And they're asking us in part 2 to identify one other type of salt that can be formed from the reaction between dilute sulfuric acid and sodium hydroxide. No, all right, so part 1 or number 1, part A of number 1. Students were required to prepare a sample of the normal salt produced when aqueous sodium hydroxide reacts with dilute sulfuric acid. So, all right, sulfuric acid is a diprotic or a dibasic acid. Every 1 molecule of sulfuric acid, we will get 2 H plus ions, or for every 1 mole of sulfuric acid, we will get 2 moles of the H plus ion. So 1 mole of this gives us 2 moles of that. So we say it's diprotic. Now, when all of the H plus ions are replaced by a metal or ammonium ion, we get what we call a normal salt. So we'll just write that. All right. And part 2, identify one other type of salt that can be formed from the reaction between dilute sulfuric acid and aqueous sodium hydroxide. So if it's not a normal salt, then it is what we call an acid salt. Some folks will say it's an abnormal salt, but no, it's an acid salt. So there we go, 3 marks down, just like that. So we're on to part B. The normal salt was produced by conducting a titration. The normal salt was produced by conducting a titration. The students were provided with a dilute solution of 4.9 grams per dm cube of sulfuric acid. Very important, we're given the mass concentration here. We're given 5 grams of sodium hydroxide, the base, and we're given methyl orange indicator. They carried out the procedure outlined in parts A and B. The titration results for part A are presented in figure 1. Review the procedure in part A for the preparation of a normal salt and and answer the questions that follow. Part A procedure. So 1, place 5 grams of sodium hydroxide solution in the volumetric flask and add distilled water to make 250 cm³ of solution. So this is our 250 volumetric flask. We're putting 5 grams. So we would have weighed 5 grams of NaOH, 5 grams. We're putting 5 grams there, and then we're adding distilled water to make up to the mark after we've done that. So we'd have 5 grams of NaOH here in 250 cm³ of water. All right, then from this, so we'd pour, after we invert this a few times, we'd pour in a beaker, then we pipette from a beaker and transfer this to a conical flask. So pipette 25 cm³ of the sodium hydroxide solution and transfer the solution to a conical flask. Then add 2 drops of methyl orange indicator to the sodium hydroxide solution in the conical flask. Part 4, step 4, place the sulfuric acid in the burette, pour it carefully, and titrate the sodium hydroxide solution until the endpoint is reached. Number 5, step 5, repeat steps 2 to 4 until consistent results are obtained. And consistent results are normally titer volumes, consecutive titer volumes that do not differ by more than 0.1 cm³. I believe CXC will accept the values if they're not consecutive, but really, we really want values that don't, we want values that are consecutive. That's how we do it when we're doing analytical work. Okay, so let us see what the other part of this question is asking us now. So that's the procedure for part A. All right, so this is figure 1 showing the burette readings. Now in part 1 of B, we're being asked to complete table 1, which will show in a little while by using the readings shown in figure 1. All right, so table 1 is showing titration of sodium hydroxide solution with sulfuric acid. So we're just going to record the readings that are here, then we're going to fill them in our table under the calculation. So the first one, we have for titration 1, we have the final reading. So we will we have the final reading. So the final reading, we're just going to write this. Let's do something colorful. So the bottom of the meniscus here is sitting exactly, well, before we even read, we always have to figure out what the gradation on this the scale is. Each of these little marks, they represent, each represents 0.1 cm³. So we're going up by 0.1, 0.1, 0.2, 0.3, 0.4, 0.5. This one is 0.5. And then here, this one, the final for the rough titration is 25.5. So the initial is 0.5, the final is 25.5. So we're making a note of those. For the titration 2, the initial is 12.2, and the final is, this looks like 37.3. Titration 3, the initial is 15.5 and the final is 40.5. So we're just going to make note of those and we're going to write them in our tables, do our calculations. So let's just pull up the table. Okay, so let us just fill out our readings. So final reading titration 1, we said it's 25.5. Initial 0.5. So the volume used would be the final reading minus the initial reading. So that would give us 25.0. Titration 2, this was 37.3, 12.2. The difference between those two is 25.1. Titration 3, 40.5, and initial 15.5. The difference there would be 25.0. Now, for part 2, we're to indicate using asterisk the titration volumes that will be used to calculate the average volume of sulfuric acid, right? Right, so let us do that. So here if you work with the 25, they'll accept it. However, we normally, for analytical work, we want consecutive readings that don't differ by more than 0.1. So since the first one was considered the rough one, it doesn't necessarily mean we can't use it. But in this case, in the case here, we have titration 2 and 3 that don't differ by more than 0.1. So we could just average those two. However, as I said earlier, if you decide to average 25 and 25, they will give you the mark at CXC. All right. So in the next part, we would actually show the calculation, and of course, if we're going to show it, we have to do it properly. So it would be 25.1 plus 25.0.0. All of that divided by 2. All of that is in bracket divided by 2, and that would give us 25.05 cm cube. So that would give us a mark. We don't want to lose our mark, so we are careful to ensure that we put the bracket to say we're adding the volumes, then we're dividing by 2. We have to bear in mind the order of operations here. So in part 4, we're being asked to complete the procedure for part B by stating the steps required to obtain a dry sample of the normal salt. So they've given us 2 steps. They've given us 2 steps here. Pipette 25 cm cube of the sodium hydroxide solution, and transfer the solution to a conical flask. 2, using the burette, add the volume of sulfuric acid used to neutralize the base from part A to the sodium hydroxide solution in the conical flask. So the volume that we used was 25.05 cm cube. And as I said, we could have worked with the 25. So in step 3, we just want to continue and to the point where we're going to get a dry sample of the normal salt. All right, so the normal salt we're looking at here is sodium sulfate. We never mentioned it earlier on, but we're looking at sodium sulfate. So we're taking the simplest route, 2 steps left. So at the end of the titration, everything is in the conical flask. The first time around, we use a screen methyl orange to tell us when we would need to stop adding our acid to the base. Now in part B, we need not use the indicator because we already know what the volume is that will totally neutralize our base. And furthermore, if we were to add an indicator, then we would not have a pure sample of our salt. The indicator would be acting as a contaminant. So I think the question will more than likely ask us about that a little later on. So that's why we don't really use the indicator this time around. So step 3, we would need to transfer contents of conical flask to an evaporating dish on a water bath, or we could just simplify it. right? So this will then set this on a water bath, and we will just evaporate the dryness. We could say gently evaporate, but the fact that it's on a water bath, that denotes that it's gentle. Evaporate to dryness. So that will give us full marks, and that's 2 marks, 2 more marks to our tally. Part 5 of B. Write a balanced equation including state symbols for the formation of the normal salt from sulfuric acid and sodium hydroxide. So here we go. Sodium hydroxide, that's an alkali, so that's aqueous. Sulfuric acid, H2SO4. And this will give us the normal salt is Na2SO4. All sodium salts are soluble, so that would be aqueous. And that's water, which is a liquid here. Now our sodium should be jumping out at us. We have 2 on the right side, 1 on the left, so we put a 2 right here to fix that. When we do that, everything that comes after the 2 for sodium hydroxide is times 2. So we'd have 2 O there, and we'd have 2H. So that means the total number of hydrogens on the left-hand side is now 4. 2 from the NaOH and the 2 from the sulfuric acid. So to fix this, we need to put a 2 in front of the water. So we now have a total of 4 hydrogens on the right and a total of 4 on the left. The sulfate is still intact, so we need not adjust that. We need not trouble that. That's fine. So everything is balanced right here. Now in part 6, we're to calculate the number of moles of sulfuric acid used to neutralize the sodium hydroxide. Now earlier on, we were told that we were given 4.9 grams per dm cube of sulfuric acid. Now that's the mass concentration. We know that from our calculations earlier, we used 25.05 cm cube of this very same sulfuric acid solution. So first things first, we know that the mass concentration we were given is 4.9 grams per dm cube. So what we're gonna do first, we're gonna convert that to moles per dm cube. So we could say molar concentration here, big M, is equal to the mass concentration that we're given, 4.9 grams per dm cube, and we're dividing that by, we're moving from mass to moles, so we'd have to divide by the molar mass, which is 98 grams per mole. Of course, grams will cancel out grams, and we'll be left with moles per dm cube. So this would give us 0.05 moles per dm cube of our sulfuric acid. Now, this is the molar concentration. In other words, we're saying that 1000 cm cube of this solution contains 0.05 moles. So if we use 25.05 cm cube, we want to find out how many moles in that. Now, we could just tell them that the number of moles of the sulfuric acid used, H2SO4, would be equal to, we take the concentration, 0.05 moles per dm cube, and we could now multiply this by the volume that was used, but the volume that we use must be expressed in dm cube here. So to convert the 25.05 cm cube to dm cube, we divide by 1000. So we could just say this is multiplied by 25 cm cube, but we're going to convert it to dm cube by dividing by 1000. And we could have just done that before and just say, hey, this is 0.05 times 0.02505. But whenever we do that, our answer will be 0.00125.
moles, or we could have written it in standard form as 1.25 times 10 to the minus 3 moles. All right. So some folks prefer to write out the statements. That's fine. That works as well. We could have here said, okay, since this is the molar concentration, we could have said 1,000 cm cube of the sulfuric acid contain 0.05 moles, and we sampled 25.05 cm cube of the same solution. So how many moles will we have present? Of course, we cross multiply, so that would give us 1,000 cm cube times x is equal to 25.05 cm cube times 0.05 moles. Of course, we'd need to divide both sides by 1,000 cm cube to make x the subject. We divide the left side by 1,000 cm cube, we do the same thing to the right side, because anything we do to one side, we have to do it to the other side. This cancels out, and we're left with the same thing we have over here. Very same thing, right? We end up with 25.05 cm cube being divided by 1,000. Cm cube cancels out cm cube. We're left with moles, and we end up with the very same thing. Just another way to approach it. And then the final thing now, final part. All right, so we're at part 7 of B. Calculate the mass of the normal salt expected from the reaction. No, just to recap, from the question above, from part 5, we wrote the balanced equation for sodium hydroxide reacting with sulfuric acid. No, in part 6, we calculated the number of moles of sulfuric acid that reacted from the volume that we used, and we said it was 0.00125 moles of sulfuric acid. All right, so this is the number of moles of H2SO4 that we have, sulfuric acid. Now, we are concerned here with the mass of the normal salt that's expected. Now, our sulfuric acid is our, in this case, so our sulfuric acid is our standard solution. We knew its concentration from the get-go. And we determined that we have a set amount of it, a set number of moles of it from the 25.05 cm cube volume that was used. So if we have 0.00125 moles of sulfuric acid, we can use the mole ratio of how the acid react to form the salt to actually determine the number of moles of the salt that we'll actually get. So should have probably stated this first. If we look right here, we're seeing that nothing is there, one is there, but we don't normally say the one when the coefficient is one. When we're talking in math, when we say we have x, when we have x, the coefficient is normally one. So in like manner, we have a one right here. So we have a 1-to-1 ratio of the sulfuric acid and the salt, the normal salt. So if we have 0.00125 moles of sulfuric acid, we will get the same 0.00125 moles of the sodium sulfate being formed. So what we need to do now, they ask us to calculate the mass of the normal salt. We know the number of moles of the normal salt. So we would now need to just convert that to convert the number of moles that we have to to mass or to grams, and we would do that by just multiplying by the molar mass. Now we'd get some marks here for calculating the molar mass of the sodium sulfate. We did not show how we did it for sulfuric acid earlier, but we should show our working. So here for the Na2SO4, it would be 23 times 2, which is 46. 32 for the sulfur, they gave us the RAM, so we'll work with those. So that's 32 times 1, that will give us 32. And then we have 16 for the oxygen times 4, which is 64. And there we have it. This would be 4 plus 2, 6 plus 6, 12. We carry 1. 6 plus 3, 9, plus 4, 13, plus 1, 14. So the RFM is 142, but the molar mass is 142 grams per mole. So the mass of the sulfuric, the mass of the sodium sulfate, the normal salt, the mass of the normal salt that would be formed would be equal to the number of moles, 0.00125. For those who want to call it 1.25 times 10 to the minus 3 number of moles, that's fine. And we're multiplying by the molar mass, which is 142 grams per mole. I'm going to punch that in. That should give us 0.18 grams. And then for the final mark to top up that 25, part 8, the actual mass of salt obtained by the student was 0.09 grams. Wow, that's half the amount that we expect, half the mass that we expect. Percent yield suggests one possible reason for the difference in the expected mass of the salt and the mass obtained. So we expected 0.18 grams, but obtained 0.09 grams. Now this could be due to a few things. We just want one of them. So it could be due to impurities in the reagent. That's REAGENTS, or it could be due to loss of mass during transfer. And it could also be due to incomplete crystallization, depending on the approach you took to actually getting the crystals in the latter part. So any of those three would give us the full marks there. And just like that, would have 25 marks.
And just like that, we've come to the end of this session. Remember, if you found value, like, share, and consider subscribing. No, copper later.